Welcome to this tutorial video. In this video we'll be looking at any changes in a mass spring system. We've got here a lovely picture of a couple of physics lads looking at a spring that's being supported by a retort stand and a clamp, and on it we have a mass system. At this position it's completely at rest, no stretch. Second picture we find the mass has been dropped halfway down its extension. Third picture is the mass system is fully extended. So let's have a look at the physics of this. Okay, here's our video. Let's have a look. First of all, for this video, we'd consider the fact that we have here a reference grid, like a normal XY, and when this video is completely round, we find that this is its resting point. The mass has fallen all the way to the bottom, so we refer to that as our zero reference point. So when we take our mass right at the top again, we find that this is now some distance above a positive displacement. In fact, I think it's about 66.5 centimeters above our final position that it falls. We'll get rid of that. So we can play this video. You'll see here we have a graph of this displacement in Y. Remembering this is the Y, the vertical axis. So let's play this and see what happens. This is working at a frame rate of 240 frames per second. So it's a great slow-mo video. We can see here that the object is falling quite rapidly at this point. And then it starts to slow down, as can be viewed each frame with our video as well. And then finally it reaches the bottom and creates a velocity of 0. Okay, let's check out some reference points. At the top here, you'll see that we have not a very steep gradient. Okay, what we have at this point is a slow rate of descent. Okay, if we look at 0.05 of a second, we see that it's only dropped a smaller amount in a time interval of 0.05. Whereas at this point here, further down, we see that now in 0.05, 1 unit across on the graph, 1 unit across, it's dropped effectively double the distance, like from 0.5 to 0.4 of a meter, 10 centimeters in 0.05 of a second. And it maintains that type of speed further down until you get past the halfway mark. Now at this point you find the distance traveled in 0.05 of a second is actually less. It's starting to reduce, and eventually it's getting less and less again. This makes sense because at the top the object is almost free falling with very little resistance to the spring. It's speeding up, and in the middle the spring starts to stretch in such a way that it retards the rate at which it's falling. Okay, and it's covering now, as there's tension in the spring, it's covering less distance per unit of time. Okay, in terms of velocity, let's have a look at this. This is the pattern we get. So let's take this back and play our velocity graph. See, it's getting faster off this graph and faster, minus 0.1, 0.2, 1.4, 1.6, and it gets to about this point at halfway, where we pause. At halfway, here we find that we've got a maximum velocity at about 1.8 meters per second, and it's negative because it's falling downwards towards our original point of origin. So it's sped up, sped up, sped up. After this point again, the tension in the spring works against the rate of acceleration, and so what happens is it was negative 1.8, it's negative 1.6, it's slowing down, negative 1.4, negative 1.2, and so forth. It slows right down to 0. Okay, if we were to look and analyze this particular velocity graph, sorry, let's have a look. Analyze. Having some fun and games on this one. Here we go. If we were to analyze, what we can find is we can look at the rate of change. So when this object was originally falling, this is the velocity in the y plane. We find there's a gradient here. Let's go over here somewhere. There's a gradient here of about 9.3. It's negative because it's falling downwards. About 9.3 meters per second per second. That's the rate of change of the velocity. It's almost free fall. It keeps on falling down, and we find the gradient a little bit further along is a value of about 5.5. So it's slowing down, and then eventually in the middle here we get a gradient, say, of 1.4 by 10 to the negative 1. It's only 0.1, nearly 0. It's reached its maximum velocity. Then we find on the second half, we've now got a gradient of 3 meters per second. It's actually this time slowing down. It accelerates up to 6 meters per second back upwards. That all matches the pattern we expect. Okay, let's analyze some particulars. So moving on, let's consider the energy. In a spring system like this with a mass, there are only three forms of energy. You've got a gravitational potential against a reference position down the bottom. You've got kinetic energy when the spring and mass system is moving. And you've got elastic strain potential energy, which is stored in the spring when it stretches. Now, first of all, at the top, okay, we always consider the sum of those three forms of energy. At the top, we've got full gravitational potential, mgh, because there's a height of 66.5 centimeters. We find that we have, following this calculation, mgh, 0.652 joules of energy. There's no kinetic, it's not moving. There's no elastic strain potential, it's not stretching the spring. So at the top, there's a total amount of energy of 0.652 joules, which is all being generated by the gravitational potential energy. If we take it to the extreme, right down to the bottom, at the bottom point, we analyze the three forms of energy. Now we've got a reference height of 0, so there is no gravitational potential energy at all. Down here, 0 joules. Here at the bottom, there was no movement. It's momentarily stationary. So there's 0 velocity or 0 kinetic energy, which means if we're still to have the same total of 0.652 joules, and we know that's meant to be the total sum of the energy any position in this system, all the energy must now be coming from the elastic strain potential of 0.652. Okay. From that information, we can also calculate what the spring constant of the spring is. We know at the bottom the strain potential energy is equal to 0.652 joules. K is the unknown, the spring constant, and delta x we know to be 0.665. It's stretched down to 0.665 meters or 66.5 centimeters. Using the equation, strain potential energy is equal to half k delta x squared, we can transpose and find that this spring has a spring constant of only 2.95 newtons per meter. This is a side calculation that you could be asked when you're looking at the extreme stretch at the bottom. Interesting things happen in the middle. At the middle, what we find is there is some gravitational potential, there is some kinetic because it's now moving, and there is some strain potential energy. In fact, if we go back to our video before, we see that the greatest velocity actually occurs right at the middle, okay, of our motion. So at the middle, we have now a height. Instead of being 66.5 centimeters, we're 33 centimeters, so 0.33 of a meter. We can use our mg delta h to work out that in the middle we've got 0.323 joules of energy that's now gravitational potential. It's half of what we started at the top, which makes sense because we've got the same mass, the same gravity, but half the height from our reference position. We can easily now, using the spring constant, also consider that as our delta x, our extension of the spring. So a half of the k, 2.95, multiplied by the change or extension of the spring, 0.333 squared, that tells us there's 0.164 joules of elastic strain potential stored in the spring. Finally, we know these two added together, subtracted from the sum of all the energy, which is always 0.652 in this case, will give us the amount that remains in kinetic to do with the movement. So we can work that out. This total energy was 0.652 in the system, and we take away the sum of the gravitational potential and the strain potential, and it leaves us with 0.165 deficit, which must be coming in the form of kinetic energy. Remembering this is where the maximum velocity occurs. So at which point we can say the kinetic energy is 0.165 of a joule equals a half the mass of 0.1 v squared, and we can calculate the velocity at this midpoint. Special case where we have our maximum velocity of 1.82 meters per second. Some interesting physics with some interesting calculations at the top, at the bottom, and in the middle of our transition, which is what you'll be asked at VCE Unit 3 Physics when you're looking at the energy in a mass spring system. I thank you for your time and hope you've learned something about the conservation of energy in this system. Thanks for watching.